Hi everyone, in this lecture I'm going to continue chapter 8. As you remember in the previous lecture we talked about the principles of network security and a little bit about cryptography. We start this lecture by the concept of authentication. Basically the receiver of a connection always wants the sender to prove his or her identity. In this case, Alice wants to have a communication with Bob, but Bob first wants to know who he is communicating with. So Bob wants Alice to prove her identity to him, and there are many ways to do it. In the simplest case, we can assume that Alice can simply say, "I'm Alice." But this will not work, obviously, because the intruder can say the same thing to Bob, can say, "I'm Alice," and Bob has no idea who said, "I'm Alice," the real Alice or the intruder. As you see here, in this slide, the intruder can say, "I'm Alice," and since we are in a computer network, Bob cannot see Alice, so Trudy can simply declare herself to be Alice. So obviously, the protocol AP 1.0 cannot provide authentication in a computer network. So let's make the protocol AP10 a bit more complicated to see whether we can provide authentication or not. In this protocol, Alice sends her IP address along with the message "I'm Alice" so that Bob can find out who has sent the message with which IP address. But again, this will not work. In the next slide, you see the failure scenario. So in order to show the failure scenario of AP 2.0, look at this figure. As you see, the intruder can simply record Alice's message and replay it for Bob. So basically, Trudy can create a packet spoofing Alice's address, although the packet is originated at Trudy, but Trudy can put Alice's IP address in place of her address and send it to Bob, so Bob has no idea who has sent the packet to him. So this is another try for providing authentication in this protocol, which we call it AP 3.0. Alice not only sends the message "I'm Alice," but also sends her IP address and her secret password, and then Bob replies, "Okay," with the Alice's IP address, but again, this protocol doesn't work properly, and we'll see the failure scenario in the next slide. Again, the failure scenario is a playback attack in which the intruder records Alice's packet and later plays it back to Bob. So this way, Bob has no idea who sent the message, either Alice or Trudy. Therefore, the protocol AP 3.1 doesn't work. As another try, you can see in this protocol AP 3.1, Alice encrypts her password before sending it to Bob, but again, this protocol doesn't work because of the same playback attack. As you see in the playback attack, in this case, the intruder intercepts the Alice's message to Bob and then plays it back later, and Bob see the same message but doesn't know who the original sender is. In order to improve protocol AP 3.1, we have another idea. In this case, Bob sends Alice a number that is randomly generated, and it's only used once in a lifetime. We call this number nonce, and then Alice and Bob share an encryption key, which we call it KAB, And then after Alice receives the number R from Bob, she replies with the encrypted R. The Alice has to encrypt it using the shared key and then send it back to Bob, and then this way Bob will realize that will prove that Alice is live, and only the reason is only Alice knows the key to encrypt nonce, so it must be Alice. In this case, obviously playback attack doesn't work because R is used once in a lifetime, and the shared key is, the key KAB is only shared between Alice and Bob. The problem with AP 4.0 is that it requires a shared symmetric key that, you need Alice and Bob have to agree on a shared symmetric keys, and this requires a pre-key distribution step, and it's not the easiest way to have the authentication protocol. The best way for authentication protocol is AP 5.0, in which we use the concept, the idea of number nonce, but we use public key cryptography instead of symmetric key cryptography. So as you see in this figure, after Alice claims that she is Alice, Bob replies with the number nonce, and then Alice, which has a private key, encrypts R with her own private key and sends Ka minus of R to Bob as a reply, and then after that Bob asks her about her public key, and then she replies with her public key. Now after Bob receives both the public key of Alice and the encrypted R, Bob calculates Ka plus of Ka minus of R, in which you have to apply the public key of Alice to the message that you got from Alice, and then it compares it to he compares it to the random number nonce R that he created originally, and then if these two numbers are equal, he realized that he proves that only Alice can have the private key, and obviously Alice has to be live, and therefore we can authenticate the sender of a message using AP 5.0. Although protocol AP 5.0 can successfully avoid the playback attack, but we can have a man-in-the-middle attack, or woman-in-the-middle attack in this case. So let's look at the man-in-the-middle attack. Trudy poses as Alice to Bob and as Bob to Alice. So Bob thinks that Trudy is Alice, and Alice thinks that Trudy is Bob, but Trudy plays two different roles in this connection. Let's see the failure scenario. So Alice first sent the message of Alice to Bob, but the intruder intercepts it at the middle of the way, and then forward the same message to Bob using her own IP address. Therefore, Bob responds to this message by sending the value R to the intruder, because Bob had no idea who sent I am Alice message to him, and he thinks that the sender of I am Alice is Alice, so he replies to the same IP address by the number R, and then in this point the intruder encrypts R with her own private key, which is K minus T. So K minus T is the private key of intruder, not Alice. And then after encrypting R, she sends it back to Bob. And then Bob again asks her for her public key, and intruder replies with her public key, K plus T. So meanwhile, intruder has to play another role while communicating with Alice. So the intruder replies to Alice by sending her the random number R, and then Alice replies with the encrypted R. Alice obviously uses her own private key Ka minus to encrypt the number, and then after that the intruder replies by asking Alice for her public key, and then Alice replies with her public key. Now at this point Bob thinks that intruder is the person that is called Alice. So Bob starts sending the intruder messages that are encrypted with the intruder's public key, and then obviously the intruders can decrypt those messages by applying her own private key, and after the intruder gets those messages, she can again encrypt those messages with Alice's public key, and then send forward the messages back to Alice. And then Alice also can decrypt those messages by her own private key, and this way the message that Bob intends to send to Alice not only is delivered to Alice, but also it is delivered to intruder. So that's the point of man-in-the-middle attack. Alice doesn't know that the messages are leaked to the intruder, but and then everything seems to be normal. But in this, as you see here, all the messages that Bob sends to Alice will also be received by the intruder, and that's the security hole of AP 5.0. So as you see, the man-in-the-middle attack is very difficult to detect because Bob receives everything that Alice sends, and vice versa. However, the problem is the intruder receives all the messages as well. Next, I focus on digital signatures, which are cryptography techniques that are analogous to handwritten signatures. Obviously, digital signatures will help to the process of authentication, but also they're beneficial for message integrity. So a good digital signature should be verifiable and non-forgeable, which means the recipient can prove to someone that Bob and no one else must have signed the document. A very simple idea for digital signature is to sign your message with your private key. For example, in this example, Bob signs a message M by encrypting with his private key KB minus that will create the signed message KB minus of M. So whenever Bob wants to send the message M, it sends it along with the signed message, which is KB minus of M. So when Alice receives the message M with the signature KB minus of M, Alice can verify the signature by applying the public key of Bob, which is KB plus, to KB minus of M, and checks whether KB plus of KB minus of M is equal to M or not. If it's not equal, then something is wrong. Either the message M is not what Bob has sent, or maybe someone else has sent the message. So either we disprove the authentication of the message, or we disprove the integrity of the message. But if they're equal, it means that we have message integrity and we have authentication. So Alice can take M's signature KB minus of M to court and prove that Bob signed M. As we talked about in the beginning of this chapter, encrypting messages is usually a computationally expensive process, and then since we do encryption a lot of time for different purposes like authentication and signing a document, or for example encrypting your messages so that we avoid man-in-the-middle attack, or a sniffing attack or a spoofing attack. We need to have a efficient way of encrypting messages, because if it's computationally expensive and you do it all the time, it makes the whole process of internet communication very inefficient. An idea to decrease the computational complexity of encrypting is to make the messages smaller by hashing them. The process of hashing is done by selecting a hash function, in this case h, and applying it to the message. So if you have a large message, usually the hash of n would be a much smaller piece of information. And then another benefit of using hash functions is that the result would be a fixed length, easy to compute digital fingerprint. And as you probably know, hash functions are many to one, despite what we have for private key or public key, which are one to one. But here hash functions are many to one, which means that the space of a domain, the domain space, is much larger than the codomain space for that hash function. Also, since hash function is many to one, obviously it's impossible to find the inverse function of h. Therefore, if you have the message digest x, then it's computationally infeasible to find m such that x is equal to h of m. We have already talked about one of the hash functions in the previous chapters. The hash function was internet checksum. If you remember, we said we can find the checksum of any large message by just dividing the message into 60-bit pieces, and add all of those 16-bit pieces all together to construct their total summation, and the total summation would be 16-bit integer. That would be called the checksum of the whole message. And obviously it's a many to one correspondence between the message and the checksum. However, it's not a good crypto hash function, because if you have a hash function and a hash value of a certain message, it's easy to find another message with the same hash value. You can simply twist the message a little bit so that the message is different, but the hash value is still the same as the original message. So it's not pretty safe to use checksum as a crypto hash function, but there are many other hash functions that they use for a crypto hash function. So let's see how hash functions can optimize the process of digitally signing a message. So instead of signing the actual message, we sign the message digest that is produced by the hash function. So in this example, look at this diagram. We have a large message like m, and we apply the hash function h to it to create h of m. It's a fixed length, smaller piece of information. And then we use like Bob's private key to encrypt the hashed message, the message digest, and this will give us a signed message digest. So in the receiving side, when Alice wants to verify the signature to see whether Bob has sent it, or Alice wants to also see the message integrity and wants to check the message integrity and see whether the message is altered at the middle of the way or not, she can simply use that hash function again. The hash function is public, everyone can see it, so she can also use that hash function and apply it to the received message M to get the hashed value of the received message, and then she can also apply the Bob's public key, which is public to everyone, including Alice, to the encrypted message digest, or to the signed message that we talked about Bob created before. And then if you apply the public key of Bob to this kb minus of h of m, you'll get h of m. So if everything is perfect and we have no message alteration in the middle of the way, and if Bob is the person who has sent the message, therefore these two has to be equal. In the case that these two are not equal, that means that either we don't have message integrity, or we have failed to prove the message authentication. If you remember, the protocol AP500 had a security hole, and the security hole wasn't preventing the man-in-the-middle attack. So to solve that problem, we showed you how to sign the messages before sending them out, so that it helps the authentication process and also the message integrity. But signatures alone do not solve the problem of protocol 5.0. We need to have a certification authority to bond the public key of every person to that person, so that, for example, if Trudy wants to claim that the public key of Bob is the public key of Trudy, so no one believes her, because there would be an authority, there would be a certification authority that can verifies that Bob's public key is Bob's, not Trudy's. So certification authorities basically bind the public keys to a particular entity. By entity, we can either have a person or a router, depending on the application. So any entity can register its public key with the certification authority. To do this, the entity has to provide proof of identity to the certification authority, and then certification authority creates a certificate binding the entity to its public key. And the certificate has a signature of certification authority, because the certification authority signs the certificate with its own private key. So the KCA minus will be applied on the certificate, so that no one else can claim that the certificate is fake, because the certificate has a signature, the signature of the certification authority, and anyone who wants to see what's inside the signed message, they can apply the public key of certification authority to the encrypted data in order to decrypt it and see that the certificate is a genuine certificate, and it contains the information which proves that entity E, for example, has a specific public key. So if Bob has a certificate, then whenever Alice wants to find out Bob's public key, she can simply get Bob's certificate and then apply the certification authority's public key to Bob's certificate, and this way she can decrypt the certificate and gets the Bob's public key. Next, we talk about how to secure emails. Let's consider a scenario in which Alice wants to send an email to Bob, but wants to send it through a secure connection. So in order to secure the connection, Alice first generates a key, which we call it KS. That would be the shared symmetric key, which is private, and only Alice and Bob will know it, and no one else know it. So first, Alice will create this private key as the sender of the email, and then this will help Alice to encrypt it, and then Bob has to have this key to decrypt the message that Alice sent to him. So Alice has to share this key along with the message that she wants to send. So in order to share the key KS to Bob, Alice has to also encrypt that key itself. So Alice used Bob's public key, which is KB plus, and apply Bob's public key to the key KS. And this way she can encrypt KS so no one else can see the private symmetric key. And Alice sends this encrypted private key along with the encrypted message encrypted by the shared symmetric key. And then on the other side, when Bob receives the message, Bob can simply apply his private key KB minus to the KB plus of KS in order to retrieve the symmetric key, which is KS. It's the one that was private, and only Alice and Bob have it now, and no one else can have access to it. And then using this KS, he can decrypt the message M by applying KS again to this encrypted message and retrieve the message M. Now, if you remember, we said we can use hash functions to make the process of authentication more efficient. So here, let's assume that we show this idea in picture. Look at Alice that wants to first use the hash function H to hash the message and create a message digest, and then after creating the hashed message, she will apply her own private key on it to sign the message digest, and then she signs the message digest along with the message through the internet. And on the Bob side, on the receiving side, Bob can simply apply Alice's public key to the signed message digest to retrieve the hashed message H of M, and then also, since the hash function is public, he can apply the hash function to the message that he receives from Alice, and then compares this H of M with the H of M that he got it by retrieving, by unlocking or decrypting this message. So if if the result of comparison show that both hash messages are equal, then Bob can prove that we have message integrity and authentication in this connection. And please note that when we say Alice sends M along the internet, we don't mean that Alice sends the message in plain text. Obviously, Alice used the the idea that you described in the previous slide, to encrypt the message properly and then send that to Bob. So if you combine the two previous ideas, you see that Alice uses 3 keys in the process of sending an email. One is her own private key, the other is Bob's public key, and then the last one is the newly created symmetric key KS. Next, we'll talk about SSL and how it can secure TCP connections. SSL stands for Secure Socket Layer, and it's widely deployed. It's a widely deployed security protocol, and it provides confidentiality, integrity, and authentication. Its original goal was for web e-commerce transactions in which people transfer sensitive information through the internet, and then also one of the goals of creating SSL was for web server authentication and for encrypting credit card numbers. SSL is a layer between TCP and the application layer. In fact, SSL gets the services that TCP provides, and then will serve application layer by a secure connection. Similar to internet programming techniques that we learn in the third chapter, SSL also provides some programming interfaces, and you can use C or Java SSL libraries to write the programs that use SSL secure connections for transferring information. The basic idea of SSL is that basically a message should be hashed in the sender side, and then the message should be encrypted by the private key of the sender, and this will create a digital signature of the message, and it should be sent along the message itself. However, in order to avoid any eavesdropping attack, you have to first apply the shared symmetric key to both the message and the signature of the message, so that no one else can find out what the message is at the middle of the way. So this encrypted message and the signature will be accompanied by the encrypted secret key. The secret symmetric key, which is used for data communication in SSL, has to be encrypted by the public key of the receiver, so that when the receiver receives the message, can retrieve the symmetric key KS and can decrypt the message and the signature of the message, and can find out whether the message is authentic or not. So if you consider a simple secure channel like a simple SSL, a toy SSL, the first step of this protocol is the handshake phase, in which both sides, in this case Alice and Bob, use their certificates and private keys to authenticate each other and exchange shared secret. And after that, they use their shared secret to derive set of keys, and then after they find the keys, they start exchanging data. But the data has to be first broken into a series of records before being transferred, and then at the end of the connection, they have to close the connection using some special messages to securely close the connection, because this way no one else can break the connection except the sender and receiver, except both ends of the connection. Here is a simple example of handshaking in SSL. As you see, first Alice say hello to Bob, and then Bob responds with the public key certificate for the authentication purpose, and then after after Alice authenticates Bob, then Alice encrypt the master secret by Bob's public key and creates the encrypted master secret EMS, and then sends it to Bob. After the handshaking step, Alice and Bob start exchanging messages. Obviously, they have to encrypt the messages so that they remove the possibility of eavesdropping attack. And then also you note that the data has to be divided into pieces before being exchanged between the parties involved in the connection. And the last topic that we consider in chapter 8 are firewalls and IDS. Basically, firewall is a router that isolates an organization's internal network from a larger internet, allowing some packets to pass and blocking others. In simple words, you can think of firewalls as a filtering tool that allows some packets to pass and reach to the local area network, to a LAN, and doesn't allow some others, and simply blocks them and drops other packets. So the motivation of using firewall can be either preventing denial of service attacks. As I said before, flooding is an attack that can be prevented by this firewall, which is a filter that doesn't allow SIM flooding be as destructive as it can be when there is no firewalls. And then also firewalls prevent illegal modification and access of internal data. For example, if we are going to defend CIA's homepage from malicious activities and malicious attackers, we need to have a firewall so that the attacker cannot replace CIA's homepage with other homepages. Another motivation of using firewalls is to allow only authorized access to inside network. For example, you can set the number of policies so that you can ban some users from accessing your network and grant access to some authenticated users or hosts. There are three types of firewalls that we discuss in this chapter. One is stateless packet filters, the simplest one, and then we have stateful packet filters, and finally we have application gateways. In a stateless packet filtering, the firewall simply decides whether to allow a packet to be either come into the local area network or depart the local area network. And this decision is made based on the source IP address and destination IP address of the packet. Also, TCP and UDP, source and destination port numbers, affect such decision, and then ICMP message type and TCP SYN or ACK bits can also be decisive in the point that whether the firewall router allows specific packets to come in or get out of a local area network. As an example of stateless packet filtering, you can consider this table. For example, if you want to drop all, if you want to have no outside web access, you can drop all outgoing packets to any IP address with port 80. So you have to look at the port number, and then if it's 80, you have to drop them. This way you can have no outside web access. Also, if you want to have no incoming TCP connections except those for institutions, public web server only, then you have to drop all incoming the TCP SYN packets to any IP except the IP of the institution with port number 80. And then you can see other examples for yourself. In contrast with the stateless packet filters, we have a stateful packet filter. For example, there are some firewalls who can track the status of every TCP connection. This way, they know whether a connection set up or teared down has been occurred by tracking the SYN and FIN messages, and they can determine whether incoming or outgoing packets make sense. Either they are from ongoing TCP connection, or they are from an old or non-existing TCP connection. And then using stateful packet filters, you can drop the packets that are from inactive connections. The third type of firewalls are application gateways, which filter packets on application data as well as on IP and TCP UDP fields. So if you remember, the other two type of firewalls didn't look into the application data, but this one not only care about the IP, TCP, UDP sections and fields. It also looks into the application data. As an example, here I'm going to talk a little bit about an application gateway that allows selected internal nodes to telnet outside and doesn't allow others to telnet with outside. To do this, we have to have first a computer, a machine that is our application gateway, plus the router that is our firewall. So first of all the telnet users have to telnet through this gateway. So if one user wants to telnet directly without sending it to this application gateway, then the router or the firewall simply blocks those firewalls, those telnet connections, because they're not originating from the gateway. But for those who send their messages through the application gateway, the application gateway looks into the application layer of the messages that it receives and only allows authorized users to forward their messages outside of the LAN. And if the user are not authorized, the application gateway simply blocks those messages. But for the other messages that come from the authorized users, the gateway simply relays them to the telnet server.